Hello, everyone. Welcome to this joint webinar by SimScale and CFturbo. I'm your host, Kanchan Garg, Product Manager at SimScale. And together with my co-presenters, Dr. Oliver Helde and Omar Abid, I'm really excited to talk about the SimScale CFturbo partnership and show you how the tight coupling between these two tools can really help accelerate your design to prototype cycle. Let me properly introduce the webinar panel first. Our first presenter is Dr. Oliver Helde, VP and Senior Scientist at CFturbo. Oliver is a mechanical engineer by training with over 3 decades of experience in turbomachinery, fluid dynamics, and software development. And he has been instrumental in developing the CFturbo software as we know it today. And throughout this distinguished career, he has worked with many companies, many turbomachinery companies across Europe and America. Oliver, thank you so much for joining us today. Just like our audience, I'm sure I am very excited and looking forward to your presentation.
Oh, thank you very much, Kanchan. And also thank you for the nice introduction. It's really a pleasure of mine to present CFturbo together with SimScale today. And I'm also very excited about this event. Thank you.
Thanks, Oliver. And our next presenter is from SimScale, Omar Abid, who is an aerospace engineer by training. And in his research career, he has worked on many projects related to turboprops and gas turbines, the experience that he brings to SimScale. And these days, as a customer success manager at SimScale, he's helping our customers be really successful in leveraging cloud-native simulation across applications, across industries. And I'd also like to mention that Omar is also the chief architect behind the CFturbo integration from the SimScale side. Omar, thank you so much for being here and really looking forward to your presentation.
Thank you, Kanchan. I really appreciate it. Looking forward to it, guys.
Lastly, I already told my name. I'm Kanchan. I'm also an aerospace engineer by training, specialized in computational fluid dynamics methods for helicopters and aeropropellers, something I did for the first 10 to 11 years of my career. And now in my role as a product manager at SimScale, I'm mainly focused on driving the development and promotion of our technology for the rotating machinery industry. I'm truly honored to be here, part of this webinar, talking to you all. Let's have a quick look at the flow of the webinar just to know what to expect. For those of you who might not be fully aware of what SimScale or CFturbo are, we'll just touch upon the introduction of these tools very briefly, after which I'll talk about the SimScale CFturbo integration, the integrated design and simulation workflow, highlighting its advantages and highlighting how it is different from similar other workflows. Oliver will then take over to show us a live demo of a turbomachinery design and also how you can reverse engineer it in CFturbo, showing the connection of the design process in CFturbo to simulation in SimScale. And that part will be handled by Omar, who will show a live demo of the simulation setup, parametric runs, everything live on the SimScale platform. And before we proceed, a quick reminder to everyone that your mics are going to be in mute. If you're facing any technical difficulty, please feel free to reach out to our webinar coordinator using the chat options. And throughout the webinar, please use the questions panel to keep posting your questions, most of which we will try to address in the Q&A session at the end. As some of you might already be aware, SimScale is the world's first truly fully cloud-native simulation platform with the vision of making simulation technologically and economically truly accessible across engineering organizations, across teams, and across the product development cycle. And because SimScale is developed and deployed on the cloud, there is absolutely zero hardware footprint. SimScale users don't have to worry about things like HPC management, licensing nuances, or data storage, data download, because everything is taken care of the cloud platform that also, by the way, offers multiple physics under the same hood. So be it CFD, FEA, thermal analysis, AI-based predictive modeling, and very soon electromagnetics, all available on the cloud. And as you can see, major companies across the world are leveraging the virtually unlimited compute power offered by SimScale to broaden the use of simulation and innovate in different fields like the development of digital twins, AI-based predictive modeling or surrogate model creations, running large design of experiments for design sweeps or optimizations, you name it, all of which needs access to simulation at scale at any time and from anywhere. CFturbo, also that some of you might already be aware, is the world's leading turbomachinery design software, very, very well known for its uniquely user-friendly and intuitive approach to what I feel is rather a complex design process. CFturbo offers very nice templated design workflows for turbo machines like pumps, fans and blowers, compressors and turbines, in addition to providing custom development support. And what is amazing about the CFturbo software is that the development team from the get-go realized the importance of validating turbomachinery designs early on to understand its performance, to understand whether a designer or a user is on the right track. And that is why the entire software paradigm has been implicitly built to couple with different simulation ecosystems. And it beautifully supports different automated workflows for design, simulation, and optimization. Traditionally, though, the desktop-based simulation ecosystems that we often see come with certain limitations. For example, like needing multiple licenses to access multiple physics, lack of HPC accessibility when you need it, when you need to quickly validate your CAD designs, data and process management. And when it comes to specifically turbomachinery design and validation, the important thing is also the long turnaround times that you typically see in desktop-based tools in terms of the time it takes to generate one performance curve. So what this means is that turbomachinery designers and engineers cannot simulate as much and as often as they want. There is always this need to triage which design to simulate, which subset to optimize. Who handles the simulations? Is it just the analyst, or do we have to go through the IT management team, etc.? And that's where enter SimScale with the cloud paradigm, and all these limitations are removed. Turbomachinery designers using CFturbo can now have instant access to almost virtually unlimited simulation capability with a rapid turnaround time on results backed by high fidelity CFD analysis, and also the same license that provides access to many different physics. And so what this essentially means is that for designers, there is no longer a need to triage. Just design and simulate when you need it, as often as you need it, and keep repeating the process. And this is exactly the kind of unique advantage we want to bring to the turbomachinery industry through the CFturbo and SimScale integration. What we hope through this automated, intuitive workflow is that users can create very high quality 3D design or reverse engineer existing designs in CFturbo and immediately push them for simulation in SimScale for either design point validation or for understanding their performance across the whole operating range, literally within minutes. And while those simulations are running, continue to design and continue to deploy more simulations simultaneously on the cloud. So this kind of intuitive, automated, and extremely fast and accurate design and simulation workflow allows for generally greater automation of the entire validation process and allows for running design sweeps, optimizations, and sensitivity analysis, not just at the last stage of your product development cycle, but from the get-go, from the moment that you have your conceptual design, all the way to the point where you are ready to incorporate your turbomachinery component into the bigger system. But as they say, the proof of the pudding is in the eating. And that's why I am now going to hand over to Oliver, who will actually show you what it is like to design in CFturbo and simulate all the way in SimScale. Over to you, Oliver.
Okay, thank you. Kanchan. You should be seeing the GUI of CFturbo now. Yeah, as Kanchan already said, CFturbo is a design package for turbo machines and turbo machinery components. And contrary to any general purpose cut packages, in CFturbo, we apply latest design theory and also empirical knowledge. And also we describe the geometry in a way that aerodynamic or hydraulic engineer would like to see, which, for instance, allows him very quickly to just change blade angles rather than point coordinates and so on. But I want to show you a live demo, and that's why I'm going to start from scratch with a pump design. The central entry in the software is always the definition of a design point, and the design point is just an operating point, and that operating point should be the operating point the pump in this case should run most of the time, because we try to do a best efficiency design. So the example I'm going to show you is as follows. So I expect the pump to transport 100 cubic meter per hour. It should generate a head of 30 meter, and it should be driven by a motor with 3000 RPM. And what we at every design step provide is a certain feedback on what has been defined so far. So here, for instance, we see now the specific speed, which is a very basic and important similarity number, but we also can quickly see where the design should be located within the coordinate diagram in order to reach a decent efficiency. There are many ways to get to the design. I want to show how one could reverse engineering a design that may have been developed in the company a couple of years or decades ago. But I could also, and that's what I want to show with the example of the volute later, one can also go step by step through the design. Okay, since the impeller is the central component in such a pump stage, I'm going to start with the impeller, and I'm going to do that by loading a legacy design and try to bring it into CFturbo's parametric description. If I choose that way, the first one, of course, is to load the data I have in mind. So, of course, I have prepared something, and I have a step file of the impeller. This can be loaded into the reverse engineering design step. And initially, once it is loaded, one can just check whether the direction of rotation is correctly applied. So it seems that this was not the case. So I just change it from right to left and carry on with the reverse engineering. By the way, I could also align it to a certain axis of rotation, but that was not necessary with this design here. But of course, had to be done if the axis was not aligned with the x-axis that we expect to have to be the axis of rotation in CFturbo. The second step is to derive the contour of hub and shroud of based on that legacy geometry. And to this end, one just has to select all the patches that make up, for instance, the hub. Here, it's not necessary to have the whole, the complete 360-degree set of patches. It's just enough to have the one that runs from the minimum radius to the maximum radius, and that's what I did here. So I'm going to map that into this redesigned geometry, and I have to do that also for the shroud. And here it's easy because it's just one patch running from the inlet to the outlet, and that's why I just have to select one. And you see immediately in the lower side that this meridional contour has been derived correctly from the reference geometry. I want to have the inlet perpendicular to the axis of rotation, and that's why I just add a certain extension at the hub here, and that extension should start at a Z position of 0. And once this is done, I'm done with the definition of the meridional contour, and I can carry on with the reverse engineering of the blade. That's the third design step, and here I can define the number of blades. So the default number is exactly the one that comes also from the reference, so I don't have to change that. I could tell whether there were splitter or not. So if, for instance, would reverse engineer a compressor impeller, and I can tell on how many spans I would like to do the reverse engineering. Again, I have to select the patches that make up a blade. So I'm going to go into this 3D representation of the reference geometry and select all these patches. I don't select the fillets at hub and shroud because they are generated in a different way in CFturbo. So it's just enough to have a set of patches that are somehow connected. Okay, then I can map it to the blade, and it should appear here. And since now this would yield a couple of more calculations and approximations, there has to be an active action, and that's why it's not immediately given here like it was for the meridional contour. One has actively pressed the update design button, and then all the data are derived, which are used in CFturbo to describe the blade in a parametric way. We get here a little warning, and it tells that at span 1 and 5, the reverse engineering failed, and the reason was that I did not select the fillet patches where these spans are located. I could ignore that because the blade will be generated by extrapolating from the inner spans to both direction, hub and shroud. But I can also get rid of this warning by just applying a certain offset to make sure that the first and the last span is within the scope of these patches. So I could increase that offset here a bit, could say, okay, update the whole thing again, and after a couple of seconds I get a new representation of the reference geometry, and I get also rid of these warnings. But as I said before, that's not really necessary because the blade will be generated by projecting that inner spans anyway. If this was done, I just can click OK, and the reverse engineered component will be displayed in CFturbo in the meridional view, but also in the 3D model. It's initially, you can see here, the reference geometry is also loaded, and it's clear that, or it's well discernible that the reverse engineering process was successful. Initially, the model is not active, so I have to make it active. And initially, it's also not parametric because we just took point data, used polylines and stuff like that, rotated it in order to generate the primary flow path of the impeller. And in order to make it parametric, I have to do some, extra step where polylines, for instance, are changed into Bezier curves, which I want to do here. And the same could be done for the camber or mean line. And if I do that, then I get really a parametric model, and I can, after I have finished that, start, for instance, automatic optimization or something like that, DOE and so on. Okay, and after a couple of measures, I have a fully parametric description of the primary flow path. So let me just change the thickness distribution also to something which is parametric. And in 3D, I have a representation of the reference. What I also want to show quickly is how to add a thickness to hub and shroud, even though later on I don't want to use it in the CFD analysis of that model. To this end, I just can activate the material contour design in CFturbo and can just grab and drag around control points, or even right click on it and give them certain coordinates. I also can include, for instance, holes to just have the shaft somewhere located like that, and split curves increase the degree of for instance, Bezier curves, and by doing so, generating a geometry with any fidelity, if you like. On the shroud side, I just, before I finish that, quickly want to show you how to generate something like a ceiling, or at least a very small gap, in order to avoid too much flow to leak back to the suction mouth of the impeller. And by that, and I do that by, again, splitting the curve, setting the curve to a straight line, putting it on 50, for instance. Split it again. Okay, and if that was done, I just want to add fillet radii at hub and shroud. So for instance, 2 millimeter. And if I do so, and if I let the cut kernel finish the design, I have, after a couple of clicks and minutes, also a nice solid representation of that model. Just get rid of the reference one, and that's the one I just redesigned. But I want to run a CFD simulation, or will SimScale do it for me? And that's why I need the complete stage definition. And that's why I'm going to add an inlet pipe quickly, which is basically a stator, an axial diffuser with a certain length. So for instance, 100 millimeter. And because the rotating and the stationary part should not touch, I'm using any offset between the outlet of the pipe and the inlet of the impeller. And then we got the pipe here. And I want to do that also at the pressure side, where I'm going to add a volute. But this time I want to quickly go through the design steps. So the first one is defining the inlet definition of the volute. Second one is to tell what is the general shape of the spiral within the volute. So there could be any kind of shapes. The third design step is how these shapes are scaled with respect to the rep angle, in this case from 0 to 360 degree. Again, we apply design theory to get an initial suggestion for the customer, but of course the designer can just override it and can make his own design. Then an outlet diffuser has to be added, having a certain length or height, so maybe 150, and also the pressure flange diameter has to be defined. And finally, the cut water has to be defined, which in this case should be a fillet with a certain radius. So for instance, 2.5 or so. Okay, once this is done, the stage basically is ready, but in order to make it watertight and ready for CFD, I have to close these gaps here. I could do that by generating a secondary flow path, which means the contour of the casing around the impeller. This can be done in the same way as I did it for the material solid of hub and shroud, but I want to make it a bit easier, and we'll use a certain feature which we call CFD setup. And here we simply can tell there must be a simple connection between stationary and rotating domains, rotor-stator interfaces, and they are applied in a way as I just did it. Let me just rename the volute quickly. And then the whole model is really watertight. Another thing which is we also call a CFD setup, but this time for the volute, is we can also add a certain extension at the pressure flange of the volute, and that allows a better definition or application of boundary conditions in CFD runs. Okay, again, if I go to the 3D model and if I let the cut kernel of CFturbo generate watertight solids, I can do that by clicking on model finishing. Then you get an impression of what has been defined. Once this is ready, I can just select the material solids. There is just one material solids because only at the impeller I have added thickness values to the walls, but I can also show the fluid solid, including the virtual domains. The virtual domains are these rotor-stator interaction, and now you see it's closed and it's really watertight and it's ready for simulation. Yeah, at the beginning I said it's a fully parametric model that you define in CFturbo, and it's given, or it's described in a way a hydraulic or aerodynamic designer would like to see it. So I could immediately go to the leading and trailing edge angles, for instance, could change them, could press the update button or the OK button, and because of the parametric description, you would get a new updated 3D model ready for the next iteration or so. And that could be done to all the parameters. So here it would be the blade angles, but it can be also the number of blades, the blade thickness, diameters, stuff like that. Okay. Although we apply latest design theory, all the designs are recommended to get validated in CFD, just because the flow within such a turbo machine is very complex. You have transient effects, you may have secondary flow, you may have cavitation, stuff like that. all of that cannot be cast into an entire or comprehensive design theory, and that's why typically, and I would say always, the initial design is something which is close to the optimum, but of course not at the optimum. And that's why analysis validation is essential, both per virtual methods or at a test rig. But of course, it's much easier or much safer to do that via virtual method. That CFD methods are also always recommended. Okay, and therefore we have implemented a big list of interfaces, and one is that of SimScale. One just have to select the interface, has to tell what components should be part of the CFD run, and because I just want to use the virtual geometries as well, I have to check that as well. A certain offset is used for the generation of the CFD run. In this case, I had this 4 to 10 millimeters gap between the stationary and rotating domains, and that's why I apply this rotating offset of 2 millimeters. Then I have to tell what is the directory for the exports. I have to tell them a certain name, so we have a convention that we call all centrifugal pumps CP, and because the central similarity number is the specific speed, we also provide this number within the name. So that's why I'm going to call it CPNQ37. And what is needed to get the run in SimScale started is an API key, and that's something I quickly copy and paste. And once this is done, I'm ready to export, and that's what I'm going to do now. And what is done on CFturbo side is that both a step file is generated as well as a kind of control file for SimScale. And once this is done, the SimScale web page is open, and the import into SimScale is started, and after a couple of seconds that should be done, and the analysis of the imports will start, and ideally after a couple of minutes or so the simulation will start. In CFturbo we are done now, so that's that has been our initial design based on the legacy geometry. We have a fully parametric model now, and based on the results of the CFD, one could later on start to maybe improve this initial design. Okay, let's go back to SimScale. Now the step file is I believe it's loaded and is optimized now, and what I can do is I can share what I have done so far in SimScale with somebody I trust, and that's Omar, and that's why I want to invite him. Okay, so the 3D geometry is here, and the simulation is soon to be started, and that's the point where I'm going to hand over the presentership to Omar.
Yes, thank you for that intro, Oliver. So taking it right from where Oliver left off, I'm going to give a quick walkthrough over what that export had actually done, what it's automated for us on the SimScale platform. So here you can see I've opened up Oliver's same project that he just shared with me. So I'm able to go in and access his project. In this case, he's giving me copy access because he doesn't trust me that much. So I can so I can view what he's done within the platform here and what was automated within the CFturbo setup. So looking here really quickly, we've now kicked off a simulation that is going to begin to run here at the design point. So this is already commenced based on the design point parameters that we've defined within the global setup in CFturbo. So before I go down the list here and actually talk about what has been set up in the simulation setup, I want to also just quickly identify, in terms of the geometry import on its own, what we have done. So we can see here, this is the original flow domain that was the virtual flow domain that Oliver had imported into SimScale. Of course, all the naming conventions, like the inflow face, the outflow face, all the static stationary walls, as well as all the rotating walls of the impeller rotor have been mapped appropriately so that it's very easy for you to modify your setup beyond what's just automated for you to progress on further iterations, or if you want to set up your simulation in a slightly different manner. However, the main thing that was also done, which is related to that offset parameter that Oliver defined earlier, is the rotating region. So what this rotating region does is it defines the moving reference frame zone within our flow domain in a CFD simulation. What this allows us to do is model these rotating regions within a CFD simulation. So typically this is something that you have to do manually and create a new CAD body within your flow domain, but this process is completely automated with the CFturbo export. Now looking back at the setup that we have here, going down the list, a lot of these parameters can be modified within the CFturbo export window. For example, we're looking at working with a K-epsilon turbulence model, time dependency, that's a steady state for now. Of course, if we're working with compressors, we have a compressible flow. But going down the list here, we have our fluid material. In this case, it was water within the CFturbo project. So we'll be defining that same water material here. And then we will define our inlet and outlet conditions. These are already been defined and automated for us. So in this case, we're just working with a static gauge pressure of 0 pascals at the inlet. And for our design point, we were working with 100 cubic meters per hour. So that's just converted to cubic meters per second here for our velocity flow rate outlet. And the last important part is the rotating zone definition. So here we can see that the rotating zone is already centered at the center of rotation of the moving reference frame zone. And the axis of rotation is already defined for us, as well as the rotational velocity of that rotor or impeller in this case. Some additional properties that we can also modify and adjust within the export window within CFturbo are the number of iterations we want to simulate, our convergence criteria for our convergence residuals in a CFD simulation. And lastly, we can define how fine we want our CFD simulations mesh to be. So in this case, it's just a basic scale from 1 to 10, allows you to step back from the mesh generating process. So what we're working with here is our subsonic simulation analysis type, and working with this analysis type, which is geared for turbomachinery applications, is we're able to work with a Cartesian mesh. So we're always generating a high quality mesh within even complex geometries like a turbo machine. So we can see here that the simulation's already started to kick off. In this case, we generated around 650,000 mesh elements for our simulation, and we're already progressing through the simulation for this model. Now, instead of waiting here for a few more minutes, let me switch gears over to another project. So this was one we had already done earlier today. So looking at the same model, or a very similar one, since Oliver was reverse engineering it a little bit more free-handed, we can see that simulation took about 11 minutes or 1.5 core hours to run. And we can see under that design point run, we can look at different properties like the moment on the rotor. So in this case, we just have our moment on the z-axis. In this case, it's in units of Newton meters. We can also look at our power required, shaft power required for this rotor. In this case, it's about 8.6 kilowatts. In this case, and the convention here is it's going to be negative for a shaft power requirement, but if we're working with turbines where power is, the work is done onto the rotor, then you would have a positive power. I'll put it here. And then the last metric that's important here to look at is the pressure difference, or the pressure head that we're generating. So this is in units of pascals, so we can take a look at that as well. However, what I wanted to look at as well is beyond what we can do within just an automated run like this, is what we can get out of it. So looking really quickly at the solution fields in the post processor, we can see the completed simulation and the respective results for the simulation. Again, this only took 10 minutes or 11 minutes. So right after you're done, you can step away from your laptop the moment this is kicked off. You can log off, shut it off. It's running in the cloud. So that's what we see is happening with that other project that Oliver just kicked off. What I want to look at is the results here in our post processor. So here we can just look at a mid-plane cross-section of the pressure contours. So we can see the pressure rise along the impeller and the velocity contours within that mid-plane. In this case, we're looking at the absolute velocity contours. So if I wanted to take a better look at what the flow contour looks like within the flow passage of the impeller blades, we can convert these vectors to a relative velocity vector. So we can start to get a better idea of what's happening within that passage. Another way to take a look at that is to work with our rotational filters. So here we're looking at a blade-to-blade view. If we take a step back here, we're looking at the blade-to-blade view right along that red line that you can see there. So we're able to see the flow path within that passage and the pressure buildup along that line, and start to see if there's any adverse flow path or flow distribution effects within the inlet of the impeller or the outlet of the impeller. We can shift that. So if I shift the span that we're working with for this blade-to-blade view, I can start to look towards the outlet, or take it a step back and look towards the inlet. There we go. So that's just a quick overview of some of the things we can get out of the post processor. An additional point I want to look at as well is maybe with any of these end suction closed channel pumps. Another thing that's worth looking at, as Oliver alluded to, is the cavitation effects. So if I am interested in seeing where the pressure drops below a certain vapor pressure, I can simply define that within an isovolume. So looking at where we're under 20,000 pascals of pressure, negative pressure in reference to the inlet, we can see where we'll start to see some significant cavitation effects near the leading edge of all the impeller blades. So all this we can see within the integrated post processor here in SimScale, and really without much of a workload on the user to set it up and start. Now, one of the main metrics to look at is beyond just looking at the design point, is actually trying to understand how our rotating machine, in this case our pump, will perform in an off design setting. So if we look again at the simulation setup that was done for us, what we can always do is we can take a look here and duplicate that setup. I've already done that in advance, And what that allows us to do is take that same templated simulation setup and modify parameters if I'd like to simulate a slightly different condition. In this case, the off-design conditions I'm interested in are going to be different flow rates. So going to the velocity outlet parameter, instead of the original 100 cubic meters per hour, we can now define a curve or a parametric input for that flow rate. So if I open that here, you can see I've already predefined that. I can either define it using a CSV file, so I can define a whole long list of it, or I could just go ahead and enter these values manually and apply that parametric curve of flow rates. So that way, when we run that simulation, I'm going to be setting up an experiment of simulations rather than a single one. What that allows us to do is set up multiple simulation cases in parallel, and all of these are going to get sent off to the cloud at the same time. So I'm not waiting for one simulation to finish before the next one to start. And what this, what this automation leverages is that we've already templated that simulation workflow where the inlet and outlet is already defined, our rotating zone, and the impeller speed is already defined for us. So all I need to do is just change what I'm interested in. In this case, I'm interested in defining the curve. So I've already done that as well. In this case, instead of that 11-minute simulation, some of the runs took a little bit longer. So the total experiment took 16 minutes to run rather than 11. But again, they were all running side by side, and this is 5 different simulation cases. So if we go back to the results that we looked at for that single case, instead of looking at it at looking at the convergence of the different results of interest, now what I can do is instead look at the flow rate versus the pressure rise of the pump system. I can also do the same for the power requirement and the shaft. In this case, higher flow rates require more power, so they become more negative, as we can see here. And same thing can be done for the moment. So in this case, the torque. Again, the torque here would be negative because it's the torque applied into the fluid versus for a turbine, where it would be positive, where the fluid is imparting the torque into the rotor. I can also take a look at all of the different simulations here. In this case, let's look at the design points out, or sorry, the duty points I was simulating here were 80% to 120% of the design point flow rate. So if we're looking at 120%, which is coincidentally 120 cubic meters per hour of flow, we could take a look at the same parameters and see the convergence of these parameters as the simulation progressed along. Another thing that may be worth looking at is looking at the convergence of these parameters. So if I'm not happy with the residuals progressing far enough, I can take a quick look at that and be able to run that simulation further to a longer iteration count to make sure that I'm confident with the results I'm getting. And I can do that with all different design point or operating points that I've simulated. Another way to just to close it off here, another way I can adjust my automated templated run is I can make it a transient case. So taking that same simulation setup that I've done and going to just defining the simulation control based on a transient simulation setup versus a steady state simulation setup, essentially just defining the time steps, the length of the time steps I'm simulating, as well as the total time of simulation. Now with a 3000 RPM rotor, we want to make sure that we're simulating at least 3 rotations. So in this case, one rotation takes about 1/50th of a second or 20 milliseconds. In this case, I'm simulating 4 full rotations or 80 milliseconds of simulation time, and about 3 degrees of rotation per time step. Looking at how long that would take in a cloud setting, this one takes about 45 minutes. Of course, it's going to be a heavier duty simulation working with a transient case. But what we're able to do is now generate a time-dependent simulation where we're actually looking at the transient effects of the impeller's operation. In this case, we're still looking at the design point of 100 cubic meters per hour. But yeah, just going over to look at the results that we got out. Again, here's the results of the pump curve. So we're looking at the design point being at 100 cubic meters per hour. We're getting about 25 meters of head, so a bit lower than what we were aiming to design for originally. But again, that's because of us reverse engineering a previous design and seeing that maybe there's going to be a discrepancy with what we're aiming for within CFturbo versus what we get out of a simulation prediction. So now we know within 16 minutes of running the pump curve, of just getting out of the CFturbo platform, we're able to now know we might need to reiterate on this design and further try to push towards our initial design point that we've been aiming for. Of course, you can also see the efficiency curve and the shaft power required at the different duty points as well. What I also want to show really quickly is just some of the visuals I showed earlier, looking at what we can get out of the post-processor here. But with that, I guess this is the time to transition over to questions. Thank you guys for watching, and appreciate you, Oliver, as well for discussing CFturbo, really powerful platform for designers to work with designing their turbo machines. So I'll leave the stage to y'all. Thank you.
Thank you, Amar. Thank you for summarizing the workflow, and thank you, Oliver, for showing the design process in CFturbo and how it links to SimScale. So we have about 5 minutes to take some questions here. And the first question is about how could one get started with using this CFturbo SimScale workflow? Omar, do you mind?
Yeah. So I mean, talk to us, talk to our different teams, and we'll try to get you guys on the platform. If you're already working with us at SimScale, we'll connect you to the team at CFturbo to get access to their software and the integration that's available. If you already work with CFturbo, just talk to us and we'll get you on the platform sooner rather than later. But a lot of it is just quick setup, and you're ready to go in a moment's notice.
Thanks, Amar. And so the next question, I think maybe for Oliver and Omar to share between you. And so what different kinds of parametrizations are possible? So on both on the CAD side as well as on the simulation side, I believe.
I probably can start with the CAD side. Well, as I said, the whole stage is described in a parametric way. There is always only one parameter that is, describing a certain feature within the CAD model, and this is done in order to make sure that, for instance, if you are in an optimization cycle, that the optimizer does not, change two different parameters where one parameter is destroying the effect of the change of the other one. So basically, all the parameters that you would or that you could change in the GUI can also be changed in a batch mode, for instance. And as I said before, you will find those parameters that you would expect as a hydraulic or hydraulic designer, like blade or wrap angles and number of blades and so on.
Thank you for that, Oliver. On the simulation side, just about all the kind of parameters that you can modify can be parameterized to an experimental run within the simulation setup side. So if we're interested in multiple different duty points or flow rates, if we're interested in looking at multiple speeds of the rotor, we can parameterize that input as well. But yeah, I mean, it really is up to you. If you wanted to conduct a mesh sensitivity study, for example, you're able to kick off all the simulations in parallel for different mesh fineness levels, where you can go about it in different ways, whether you work with the automated 1 to 10 scale, or if you wanted to define the different parameters that are corresponding to the global fineness or local fineness of the mesh that you're working with. So really just up to you. It's either something you can parameterize within a table, or just as fast as you can set it up and push them to run. Yeah.
Okay. Thank you both. We do have a few minutes, and maybe we can take a couple of questions more. One question is on how do you account for roughness? Which approach are you using?
Yeah, no, that's a good question. So the roughness of your surfaces can be defined using a surface roughness parameter. What in the CFD context, these methods are, these models, excuse me, are based on experimental data collection. So if you're working with a surface roughness of 0.5 millimeter, for example, what that is actually modeling within the CFD context is it's trying to model similar studies of essentially beaded elements that have that thickness side by side for that roughness scale. So there's a lot of ways for you to get literature based on a cast iron element versus a smooth wall of how to define that roughness constant within your stationary walls. But there's some documentation available on the SimScale platform, as well as literature all over that can help you define that parameter. But it's really just a single input to define a wall roughness, which determines what's going to be happening near the walls in terms of pressure loss and turbulence.
Thank you. Thanks, Omar. And quickly, Oliver, like one final question to you. Would it be possible to design and simulate like an open impeller? Like what would be some of the considerations?
An open impeller, if an unshrouded impeller was meant, so that is intrinsic in the software. It's just a parameter to tell whether it's unshrouded or shrouded. So there was no extra need to do something extra. If something is meant like an open impeller, like a propeller or so, from a geometric point of view, from the cut point of view, there was no restriction. One would probably do that by, generating some sort of a big volume around this propeller.
Mm-hmm.
Yeah, maybe that answered the question.
I hope so. And we are at the top of the hour. Whatever questions we could not answer, we will get back to you via email, and all of you will also receive a webinar recording within a few days. Thank you for attending. It's been a real pleasure. Thank you, Oliver. Thank you, Omar.
Thank you, Kanchan and Omar, and thanks to the audience.
Thank you. It's been a pleasure. Have a great day, y'all.